This video is about sigma and pi bonding. By the end of this video, you should be able to differentiate between sigma and pi bonds, understand how unhybridized p orbitals contribute to multiple bonds, and identify sigma and pi bonds in a molecule. A sigma bond, often represented with a sigma sign, is an electron pair that is shared in an area centered on a line running between two atoms. In other words, the electron pair is between the nuclei of the two atoms involved in the bond. Single bonds are sigma bonds. All single bonds are made of sigma bonds. They're formed from orbitals that point towards each other, as shown here. Here, our two fluorine atoms have their p orbitals overlapping, and the electrons exist between the nuclei of the two atoms to form the bond. A pi bond, on the other hand, often abbreviated with a pi symbol, is an electron pair that is shared in an area between two parallel orbitals. A double bond contains one sigma and one pi bond. These are formed from orbitals that are parallel to each other, as shown here. Our pi bond is the pair of electrons shared between these two parallel p orbitals. Here we see a sigma bond with our end-to-end overlap and our pi bond with our side-to-side overlap. This is a double bond since we have both a sigma and a pi. Sigma bonds can form from end-to-end overlap of s, p, or hybrid orbitals. Here we see an ss overlap, a pp overlap, an sp overlap, and we could also have overlaps that involve hybrid orbitals, as we saw in the previous video. Pi bonds, on the other hand, are formed by an overlap of two side-to-side orbitals. These are generally p orbitals. Here you see the side-to-side overlap of these two p orbitals. Considering how each bond uses sigma and pi bonds, we see that single bonds use only sigma bonds. Double bonds contain a sigma and a pi, as shown in the example we looked at, and triple bonds contain one sigma and two pi bonds, as seen here. This is a C2H2 molecule with a triple bond between the two carbons. Here we see the sigma bond, our end-to-end overlap, and our two pi bonds, our side-to-side overlap of these two p orbitals. Recall that when we have sp2 hybridization, we're left with one unaltered p orbital. This will allow us to form a double bond. Consider the double bond between the two carbons on this molecule here. Since each carbon has a trigonal planar geometry, we know that each carbon will form sp2 hybrid orbitals to give us three equivalent orbitals. This is shown here. Here's our carbon with our three equivalent sp2 hybrid orbitals, and our one unchanged p orbital. This is the remaining p orbital left after two of the three p orbitals have been hybridized. Likewise for the other carbon. When these two carbons come together, we get the end-to-end overlap that forms the sigma bond between the two carbons and the side-to-side overlap of those unaltered p orbitals, forming the pi bond. A sigma plus a pi bond gives us a double bond. Let's consider now a triple bond, which requires sp hybridization. Again, when a triple bond forms, we need one sigma and two pi bonds. The two pi bonds will form from the two unaltered p orbitals left behind when sp hybrid orbitals form. Consider the C2H2 molecule shown here. We know that the hybridization around each carbon must be sp since they're both linear geometries. Therefore, we know that each carbon will form one sp hybrid orbital and leave two unchanged p orbitals behind from the two p orbitals that remain. Then we get an end-to-end overlap to form our sigma bond between the two carbons and two side-to-side overlaps, as you can see by the dotted lines here, that represent our pi bond. One sigma and two pi bonds gives us a triple bond. Here's a question to try on your own. Pause the video here and see if you can figure out how many sigma and how many pi bonds are in this molecule. When you come back, I'll reveal the answer. Welcome back. Here's what you should have gotten. Notice that each of the single bonds between B and H and B and C are sigma bonds, giving us 4, and our triple bond contains 1 sigma and 2 pi, for a total of 5 sigma and 2 pi bonds. That brings us to the end of this video. Let's review our goals. First, we learned to differentiate between sigma and pi bonds via the overlap in orbitals. Then we learned how unhybridized p orbitals contribute to multiple bonds. And finally, we learned to identify sigma and pi bonds in a molecule.